In this segment, we'll examine the assembly for checknum from the primes.c program. And as you can see in the notes, we've got the C code up here and the corresponding assembly down here. We'll continue with the guided tour mode. The ILQ is asking you to think through the code on your own as much as you can and to comment it as you go. So to that end, the first 5 lines here set up a stack frame. By now, they should be pretty standard, but question 1 would be, how much space does this stack frame reserve for local variables? And what are 2 of the variables, and where are they stored? Is either of them at the top of the stack frame? Well, first of all, 16 bytes is the answer on the amount of space, as you can see with the subtraction by 16 for SP. And then the offsets minus 16 and minus 20 from the bottom of the frame are storing toTest and prime set. And you can tell that, of course, because the 2 parameters are going to be in R0 and R1, as we know from prior discussion. Now, the prime set, the latter of the 2, is at the top of the stack frame in the lowest bytes of the 16 bytes that were reserved. And remember that FP points to the bottom and LR is immediately above it, followed by the local space. So the top of stack is actually 20 bytes above FP in the stack frame. All right, so on to question 2. A couple more lines to look at here. What about these 2 instructions? What do they do? What C variable is involved? And what part of the C program do they implement? If you look at it, they're really setting divisor to 2. It's the only thing being set to 2 in the C code, so that's got to be divisor. And it'll apparently be stored at offset -8, right at the bottom of the locals area, immediately above LR. And then question 3, no surprise here. Please comment these first 7 lines based on the discussion we've had. And then we'll put a reasonable answer up in the notes. And there's a reasonable answer. You can see that the initial store multiple FD is doing a store of FP and LR at the base of the new stack frame, and we point as FP to that new stack frame base where the old FP is stored. Reserve 4 words of space. toTest is just below top of stack at offset minus 16, and prime set at top of stack at minus 20, and then we store 2 into the location for divisor. Now, so far this is pretty routine, but there's something interesting going on at the next line. We've just done the initialization of the for loop, and I suppose we'd expect the code for that loop test up there to be the next thing to appear, but instead we have a BL13 instruction which does an unconditional branch past the 3 lines 121 through 123. So question 4, what do those skipped lines do? What C code do they implement? And the answer is they increment, or they do an implementation of incrementing divisor, so they do the divisor plus plus. They're implementing, in other words, the loop incrementer, not its test. So we skip over the incrementing code, arriving at the block of code starting at L13. Now, this is actually the loop test, implementing divisor less than toTest and toTest modulo divisor not equal to 0. Scroll that up a bit. So this whole thing here, our loop test. Now, if this test is true, then the BNEL15 instruction at the end of it here is going to loop back to the incrementing code, and that then leads into the loop test again. So the loop incrementer is thus done truly after the test by virtue of that loop back. And why the compiler did this, it's similar to things we've seen before, is something we'll examine in a bit. But first let's decipher that loop test. Which brings us to question 5, and that is, what does this part of the loop test do? First part from lines 125 on down to the B high here. It should be a B high HS, sorry. And 2 points to remember there. BHS is a branch if first operand is higher or same from the prior compare, and L14 is the label of the first instruction after the loop. So with that in mind, it should be fairly clear that we are comparing divisor at offset -8 to toTest at offset -16, and we are going to jump out of the loop if the test shows that divisor is greater than or equal to toTest, higher or same. So this is doing the first part of the loop test up in the C code here. Question 6. This means that the second part of the loop test might be entirely ignored if we make the jump to L14. Is that okay? And if so, why? And the answer is it's fine. If the first part of an AND is false, then the second part is irrelevant. Indeed, C, like most languages, generates or guarantees, that if the first half of an AND is false, the second half won't even be computed. And this is variously termed a short-circuited, conditional, or protected AND. So this leaves us with the second half of the loop test to be executed only if the first half was true. Now, to understand this code, you have to know that the rather lengthily named ABIUI divmod is a library function supplied by the C compiler to compute both the quotient and modulo of a pair of integers. And this is because the ARM ISA lacks an integer division and modulo operation. It's a lot slower than built-in assembly instructions would be to call a function for this, but it gets the rarely needed job done. It expects its arguments in R0 and R1, like any function, and it returns the quotient, R0 divided by R1, in the register 0 and the modulo, or the remainder, R0% R1, in R1. So, question 7. With that information, look at these lines, 129 through 136, and explain how they implement the second part of the loop test. And could you shorten them by 3 instructions? The answer here is that they pass divisor and toTest to the divmod function, but they do it in a roundabout way. First they load them into R3 and R2, there's divisor and toTest, and then they move them into R0 and R1, so we have toTest and then divisor, and then calling the function. And I think pretty clearly we could save 2 instructions by just writing, let's see what it would be, LDR R1 to put divisor into R1, and LDR R0 to put toTest into R0, and then we could dispense with lines 131 and 132 entirely. Now the instructions after the call move the modulo, divisor %toTest, which recall will be in R1, or into R3 instead, and then compare it with 0, and they jump back to repeat the loop if the modulo is not 0. And that comparison could simply have been CMP R1 #0, saving another instruction. And that result is that these instructions test toTest %divisor not equal 0, and then they repeat the loop if it's true. Otherwise, they fall through to L14 and exit the loop. Okay, and question 8 is not going to be a surprise. Based on all the discussion so far, comment lines 119 through 136. And again, you don't need to necessarily comment every line if a block of line does one simple thing, but at least make comments fairly clear for the entire block. And here's a reasonable set of comments. First, we see the 121 through 123 simply implement or increment divisor. And then, as we just said, R2 gets divisor, R3 gets toTest, and compare divisor in toTest, and then exit the loop if divisor is greater than or equal to toTest. Otherwise, R3 gets divisor, R2 gets toTest, and then pass them as parameters 1 and 2 to the divmod method, which will compute toTest percent divisor, also the quotient, though we won't look at that. And then R3 gets the result, and if that's non-zero, then back to loop. Okay, now that we understand how the loop test works, let's look more closely at why the compiler organized the loop code so oddly, putting the incrementer at the top. It did this to reduce the number of branches. If the loop test were at the top, then a branch decision would be made after the loop test to decide whether to repeat the loop or go with the rest of the program. So if the test were up here, then we'd have to decide whether to branch around. And then a branch would still be needed at the bottom, just to return back up to the top. With the iteration code at the top, each successive loop iteration needs only the one branch at the bottom. But we've talked about this already in earlier examples where we showed odd loop structure and said it was reducing branches. But why reduce the number of branches? Because the ARM processor is pipelined. We think of an assembly instruction as a single action, but performing an instruction actually takes several steps. The CPU must first load the instruction from memory, and then for a register-based operation, it must fetch operands from the registers, possibly perform a shift or an arithmetic operation, and then save the result back to a register. For a load store, it must compute a memory offset, and then read and write a register value to or from that location. Also, branches and other instructions, as we've seen, can be qualified with a GE, LT, or NE, or any other condition. So any instruction must first go through a test to see if it should be run at all. Each of these steps requires different parts of the CPU hardware, so the CPU can work on several instructions at once. For instance, loading one from memory, testing condition for another one, fetching registers for a third, performing arithmetic for a fourth, and saving results for a fifth, almost like a physical assembly line might build cars or computers. Such an approach is called instruction pipelining, and all RISC processors do it. Indeed, the main reason for a reduced instruction set is that a simple instruction set is easier to pipeline. Now, the 5 stages I just described are merely representative. The particular number of stages in the pipeline varies by the version of the ARM processor. Simpler versions use just 3 stages. Later ones use even more than the 5 stages I described. Here's a brief look at a diagram from the ARM Info Center showing a more recent ARM processor's pipeline. Now, you don't need to understand the details. Just appreciate that the CPU is running a sophisticated assembly line with multiple instructions going at a time, each at a different stage. Pipelining speeds the CPU up by a factor of 3 or more, depending on the number of stages, but it has one critical limitation. When the program reaches a conditional branch instruction, like say our BNE here, the CPU can't know whether the branch will happen or not. And it might not even know the target address until the branch instruction has made it partway through the pipeline. But in the meantime, the instructions after the branch continue to feed into the pipeline and start executing. If the branch occurs, then those instructions after it should not have been executed. And since those misloaded instructions don't save their results until they reach the end of the pipeline, the mistake can be corrected by simply dropping the misloaded instructions from the pipeline and instead restarting the pipeline at the new location that we jumped to. But this wastes time. So branch instructions are inherently inefficient because they can disrupt the smooth flow of the CPU pipeline, and compilers for RISC processors try to minimize them. Okay, so let's move on now with the rest of checknum. The instructions after the for loop implement this if statement. If divisor equal toTest, set bit, toTest prime set. So we'll go down and look at those. Or more precisely, I'll ask you at this point to simply identify the ones that implement those two C lines and explain why they work, rather than me telling you which lines those are. So, and a question to consider also, could they be made more efficient? The answer is that the instructions from L14 to L16 here, lines 138 to 144, implement the if statement. The first four lines, load, divisor, and toTest, once again, compare them, and then jump around the last three instructions if divisor is not equal, the NE note, if divisor is not equal to toTest. So the last three instructions here run only if divisor is equal to toTest. And how could we make it more efficient? If we had loaded the toTest values straight into R0 here, and then used that as the basis for comparison also, then we wouldn't have had to load it on the line 142. Okay, so moving along then, the return value is the next thing to look at. The if statement instructions are straightforward, but those for performing return divisor equal toTest here need more careful examination. And those instructions, scrolling back down again, are down here after L16. Now, the ultimate goal of these instructions is to compute the true-false value, 1 or 0 value, of divisor equals toTest, and put that value into R0, which, per the calling convention, is the expected location of the return value from checknum. The first three instructions pretty clearly compare divisor and toTest, but instead of the usual branch after the CMP instruction, we have a move EQ and a move NE instruction. Now, we've seen the NE and EQ qualifiers on branch instructions, and recall from earlier lecture that any instruction can be qualified this way and will execute only if the condition codes from a prior comp or test match its qualification. So if divisor and toTest are equal, the result of the CMP sets the Z flag, and the move EQ instruction runs. Otherwise, the move NE instruction runs. So to be exact, the CPU does load both instructions from memory, but the non-matching instruction is not run. And the net result is that R3 gets 1 or 0 depending on the CMP outcome. Question 10. Rewrite the code to use a conditional branch and simple move instructions. Is that better? And the possible answer here, one way to do it would be like this. Compare them, and if they're not equal, branch to LA and move a 0 in, otherwise fall through to the move 1 and then branch down to LB and continue on with the rest of the program. Now this is pretty clearly not a better solution. It requires two instructions in either case, and one of them will be a pipeline disrupting branch. So perhaps surprisingly, it can be much more efficient in small if-else cases to run both branches, but qualify the instructions so that one of the branches is ignored. This is especially true, of course, for pipelined RISC CPUs, for which branches are highly inefficient. Okay, the UTXB R3R3 instruction is unfortunately just compiler dumbness. This instruction sign extends the most significant bit of the lowest byte of R3 up through the entire upper 3 bytes. In effect, it does a sign extension of the bottom byte up through the upper 3. And since R3 has either a 0 or a 1 value, and they're both non-negative values, sign extension is pointless. While we're at it, you may have noticed that 4 of the 16 reserved bytes of local space in the stack frame are never used. More compiler dumbness, I'm afraid. There is no FP-12, did you notice? So we're almost done with this module, And the module on optimized ARM code will show just how smart compilers can be if they're asked to optimize code. And question 11, the last three instructions of check number right down here, 152 through 154, briefly explain what they do. And the answer is that the first instruction moves this just computed R3 value into R0 so that it can be properly returned. Compiler should have put it in R0 in the first place, obviously. The sub sets the stack pointer back to the location of LR, just above where we stored FP. In other words, it pops the local storage area off the RTS. And then the LDMFD loads LR and FP from the stack back into registers. But it puts the LR value into PC, which effectively does a jump then to the LR location. And then, not surprisingly, a final question based on all the discussion so far, comment lines 138 through 154. As before, you don't necessarily need to comment every line if a block of lines does one simple thing. And this is the last in-lecture commenting exercise we'll do. However, you should do this type of commenting on your own when deciphering assembly code in future segments. And here's a reasonable answer. So by way of review, we loaded divisor and two-test into R2 and R3 and did a comparison of for not equal. If they were not equal, we jumped around the set bit call. Otherwise, we do the set bit call by setting param1 to two-test and prime set for param2 and calling set bit. Either way, after the call, we again load R2 and R3 with divisor and two-test, check to see if they're equal. If they're equal, then the return value will be a 1. If they are not equal, then the return value will be a 0. And then do a needless sign extension, and finally put the return value where it should have been in the first place. Remove local storage, and then pop off FP and LR with LR going straight into PC. So we're going to jump back to the calling point. So that wraps checknum up. In the next segment, we'll examine the main function for primes.c.